Yeah, so I'll talk about the general method of designing FPT algorithms by exploiting LP-relaxations. And this will be a little bit different in nature to most of the talks at this workshop. I'm solving graph problems ultimately, but the actual stuff presented is to do with several things, none of them really graphs. So this probably runs better if you do ask questions when you don't follow. So, starting from the beginning, the motivating example, or almost the one example that actually works. So FPT's most classical problem, you have a graph, you want to find k vertices in the graph that intersect every edge. It has a natural LP relaxation. We minimize the sum of vertex weights, subject to having at least one vertex fractionally on every edge. And since the 70s, we have known that there are two very useful properties of this particular relaxation. The first, which most famous, is the half integrality, that this relaxation always has an optimum where every variable xv takes value 0, 1/2, or 1. And the second, which is more structural and more important to us, honestly, is, well, it's been called persistence. It says for any optimum x star of the LP relaxation, there exists an actual optimum, which, a set of vertices, which contains every vertex, which takes value 1 in the LP, and doesn't contain any vertex that takes value 0 in the LP. So if you view the values of the LP here as being not in the cover, and the middle value being I don't know, then you can trust the decisions of vertices being in or out of the cover or the vertex cover. So if you have, well, one feasible solution for the LP, of course, take everything by 1/2. A better solution for us for this particular LP, this is the same weight as the previous one. So this tells me we're allowed to delete these and throw away these, reduce a parameter by k, and do something else to these 3 remaining vertices. This gives you, this was observed 2012, this gives you an FPT algorithm. If you just want to solve vertex cover, this is not the fastest algorithm to do so, but it's illustration of what will follow. You start by the LP optimum. You pick any vertex which was given the value 1/2 in that optimum. You try to force it to take the value 1. Like you can just add this constraint to the LP and see if it changes the cost. If it doesn't change the cost, just freeze this assignment to keep searching. In the other direction, you try to freeze the same variable to take the value 0. If this does not increase the cost, you freeze it there and keep searching. Otherwise, you find one variable. You have found your one variable where both freezing it to 0 and freezing it to 1 will increase the cost of the solution. And this is now it's just a branching question. Like here you have some cost to mu, here you fix v equals 0, here you fix v equals 1. Here your cost is at least mu plus 1/2 because it's half integral. Whatever you did will increase the cost by at least an entire half. And you keep branching. So the first easiest statement is just that the height of this tree has height at most k, because eventually you run into an LP where you have to pay more than k even for the fractional solutions in backtrack. So the size of this whole thing is 2 to the k. More carefully, you start with some relaxation value mu, which is at least half, but could be much closer to k. And the height can be bounded by the difference of the relaxation and the optimum. So yeah, you can also do it more carefully and more involved than just one variable, two directions. You can pick a few variables. You can look for things which improve the value more than this. You get so this is 4 to the k minus mu, and there exists a result like 2.3 something to the k minus mu by some careful analysis. And it happens, although not really explain how, it happens that the parameter of vertex cover parameterized by the gap between the solution and the LP is kind of a tightening of parameterized by k minus maximum matching number, which happens to be equivalent to a very important problem called almost two-set. So this very simple LP branching algorithm solves, almost two-set, one of the central problems of parameter complexity. It took years and years to solve these two direct methods, and the first several versions were large and unwieldy and messy. So if you're willing to accept that we have an LP solver that we don't have to write ourselves, the description of this algorithm for almost two-set is a very short algorithm, right? So I'll give one more example which actually works. I won't go through it as slowly. So problem is node motorway cut. You have 3 terminals in this picture. So in general, at least 3. So the terminals are the thick black blobs. The rest of the smaller vertices. And if you look at this, you see that for every path between 2 different terminals passes through at least one red vertex. So the red vertices hit all paths between terminals, and to find these vertices is an NP-hard problem. This is the problem we're trying to solve here. This also has a half-integral LP-relaxation, which was shown to have the same kind of persistence property. I'll hand-wave a little bit around how this works. You can introduce some additional variables which say how far is vertex V away from terminal T. So every vertex turns into some size cardinality T different new variables. Then you have one constraint saying for every vertex in every pair of terminals, the sum of distances from the vertex to the terminals is equals 1. And the distance from V to T is not allowed to be larger than the distance of a neighbor to T plus the amount by which the V is deleted. So this is some relaxation which was known in approximation to be half integral. It was shown by Guimard in 2011 that it also has this something equivalent to the persistence property. Like you cannot trust its votes about whether to delete vertices xv or not, but you can trust its vote if it say v should be distance 0 to t, then you know that v should be connected to t in the optimum. If v is distance 1 to some other terminal t prime, you know the v is not connected to t prime in the optimum. So in particular, distance is equal to 0. If you just follow the reachable part from variables that have value 0 in the LP, you get a local region, which can be contracted and branched on. This was shown Sigam and Marcin Michał Polipchuk in 2013 realized that this LP is useful for solving multi-way cut in time 2 to the k, which is the fastest algorithm. And these are the 2 examples that you get if you just look in the literature and scratch your head a bit. So the bad news, if you try to do something like this, whatever something like this means for any random problem, you will run into problems. Most LP relaxations are arbitrarily fractional. You don't get any. You very rarely get half integrality. Even if you get half integrality, you may not be able to trust its integral values, like its zeros and ones. It's in general NP hard to check whether there is a solution, integral solution of the same cost as an LP relaxation. For example, if you try to solve SAT via an LP relaxation, you write one equation per clause, like x1 plus 1 minus x2 plus x3 is at least 1. You set every variable to 1/2 and everything is satisfied, and the LP gave you nothing. So that's an extreme example, but persistence is really hard to get, and it also hasn't been the focus of the approximation literature because persistence doesn't tell you anything about approximation values. So the approach of what I'll actually talk about in one picture is that the initial impulse when you see these two examples is to try to follow this scheme, like we will look for good LP relaxations of interesting problems and use them to design simple and fast FPT algorithms. That turns out to be too hard. So too hard for me and too hard for some of the smartest people in parameters complexity. I happen to know some of the absolute stars of the field who are actually trying to do so and just concluded, well, there probably doesn't exist anything because you don't find anything if this is what you do. So the approach, the two different variants of approach I'll sketch in the talk say, well, you don't start with the LP, you start with some condition on your problem. I'll give two different ones, like either a combinatorial or algebraic or some other condition that tells you that the problem has some good property. This condition, you can use tools from the literature to show that it has an LP relaxation, which could be non-obvious, which could be useless for approximation, but could still exist. That would have these properties like generalizations of half integrality and some persistence. And then once you created this, you can design an FPT algorithm for it. And as a possible next step, once you know this is possible, you can just discard the LP solver and attack the problem combinatorially. Like the existence of an LP solver with good properties implies that there also should exist a purely combinatorial algorithm, although it might be larger, messier, and more complex. It would also, in known cases, also be faster, like maybe you get this diverting arrow with a linear time algorithm instead of LP solver. Well, that's just the background, so I haven't actually said anything yet. I'll still ask you any questions about what I've been saying up until this point. So I'll give two approaches. One possibly more mysterious, where you phrase your problems as something called valued CSPs. And one more combinatorial, but as far as I know, more specific to just one thing, where you have some axiomatization of hitting cycles behaving in a certain way. Yep. I think the combinatorial condition I'll cover is it has to do with biased graphs. I mean, there is basically just one condition that works. I'd be happy that I know of. I'd be happy to see if there's kind of other things that work, but what I'll present in the last part of the talk is, the one example I'm aware of this.
Okay, so you propose these two variant properties as an example of this combinatorial.
Yeah, so the first one is algebraic, and I would need a bit more preamble before I can tell you why it's algebraic. Like the first one, well, views the LP as an auxiliary solver for a discrete problem instead of kind of continuous relaxation. The second one just is kind of completely different flavor. You're given a graph, you're given some oracle for good and bad paths, good and bad cycles, something like this, and then you can prove the existence of algorithms for this. So, yeah, like I said, the second one is the most combinatorial in flavor, so maybe that will appeal to some of you most, but the first one is still the one with the largest number of examples. I'll start there. So we'll think about the vertex cover LP, because that's absolutely the easiest case. The fact that the LP always has an optimum that takes values in 0, 1/2, 1 to the n means that you don't need all the other values in between. Like The linear program, of course, uses kind of all rational numbers between 0 and 1 to find an optimum, or it could. But the fact that there exists an optimum to vertex cover that only takes these values tells you that in some sense you don't need the intermediate value. So just say that if I imagine that what I wanted to solve was a minimization problem over domain 0, 1 to the v. What the LP actually solves is a minimization problem over a finite-sized domain 0, 1, half 1 to the v. And these abstract properties, the persistence property tells you can use the solutions for this to guide your search for solutions to the original. So now there's a few definitions here. Like the way I'm handling this question is something called valued CSPs. So you define your problem as fixing a collection gamma of allowed types of cost functions, and the input is a sum of applications of these functions, and your goal is to minimize, like find an assignment for the variables to the domain. The sum of the costs of all your individual cost functions is minimized. Like the problem description is not difficult, maybe abstract, but for every fixed language gamma, you get one different problem. Like formally, just which types of functions am I allowing here? It's known that for every gamma, the problem becomes either polynomial time or NP hard. There's a few results for this, like if all costs are only finite, this was known 2012. If the costs also include infinity, then some result came a few years later, and then there's the underlying version where you don't care about optimization, you just care about whether you can get any finite cost solution. This is very recently the general CSP problem, which was solved in 2017. And the link is that all cases where the VCSP is polynomial time tractable are solved by one canonical, simple to describe LP relaxation. So this is this is our hunting ground. So languages gamma for which the VCSP is tractable will be our hunting ground for the middle box of our scheme. Like this will be where we look for useful LP relaxations. And now we try to so maybe I'll just walk through a few examples just to exercise the notion. Vertex cover can be defined as the VCSP with domain 0, 1. Edges which cost infinity if both endpoints take 0, otherwise they cost 0. Saying you have to have every edge covered by a vertex, otherwise you cost infinity. And a single cost which says the cost of vertex v is the value of vertex v, either 0 or 1. So the first one is called a crisp constraint because you're not allowed to break it. The second one is kind of a soft constraint, saying it wants all variables to take the value 0, but you have to pay a little bit to break them. So this is not a generalization or a specialization. This is literally exactly equivalent to vertex cover. Just convert edges to the first type of constraint, vertices to the second type of constraint, and vertex cover is one point in the big space of VCSPs. So therefore, this language is intractable. If you instead have constraints, thin domain, variables are forced to be taken value 1, forced to be taken value 0, and there are soft constraints uv which cost you 1 if u is 1 and v is 0, otherwise cost you 0. Then if you think about this, you think about all the variables taking value 1 as the left side of a cut, all the variables taking 0 as the right side of a cut. The edges you pay for, the arcs you pay for, are exactly those that cost the cut. So this is another point in the problem space, which is a tractable point, which corresponds to optimizing graph cuts. The edge multi-way cut version, well, you can do it by a larger domain, 1 through t, and just say you have crisp assignments, and you have soft equality. Vertices want to stay together. You have to pay for every edge if they're not. And some surprise tractable cases, as I implied on the blackboard. If you just reinterpret vertex cover to take values 0, 1, half, 1, and you write down what the LP does for those, this creates a this creates a problem which has a search domain of size 3 and which is tractable. Like you can solve it through the LP, you can solve it through other means. Half integral LP edge multiple cut in the same way, just add a 1/2 value to your domain, and you get something that is a tractable problem. So these tractable problems, I mean, in these two cases, they come from looking at what the known LP does, but they also happen to have some algebraic condition that proves that they are tractable. And the algebraic condition is what we'll use to get the FPT algorithm.
Do we have a greedy to approximation for edge multiplication?
Greedy to approximation. Edge multiplication cut has approximation value, well, better than 1.5 is 1.3 something? It's a serious open problem exactly what the integrality gap is, but the best approximation LP for edge multiplication cut is, as far as we know, not useful for FPT algorithms. It's too messy, it's too fractional, things are floating around, you don't get any crisp decisions about go here or go here. So this is actually, in spirit, this is closer to the node multiplication cut LP, which is too approximate, and also happens to have the persistence property that lets us branch over it.
Okay, so you define this having the row vertex cover and vertex cover in the boxes with extended production. And proof that this is not tractable is not immediate from the visual LP-relaxation. If you happen to already know the half integrality proof of the LP, then you know it's tractable. Because in order to solve it, you just solve the LP. If you need to, you do some exchange until you're at the vertex of the LP, and this will be a solution. But there is also an alternative proof that is purely algebraic for why it's tractable. And well, you can also think about. I mean, I don't know if I'm using my time optimal for this, but maybe it could still illustrate something. Like if you define a cost function that, for example, well, that's not the, so this is just a list of values that some function takes over the possible assignments, and then you also have you also include the natural variance of it. Which did I miss? Then the language of all of these cost functions, if you think about it, is equivalent to the problem called almost two set, because each one of these forbids one specific combination of assignments, and you have to pay one for every clause you break. Therefore, this one is intractable, and the tractable relaxation looks very much like some kind of linear interpolation of this. Like if you just extend your values 0, 1 to 0s, 1s, and 1/2s, this and the same thing for the three others form a family of a tractable VCSP. There's an algebraic condition, which I won't explain, but it's called by some modularity, which proves that this function class is tractable. So this is in general what we're doing. We're starting from a smaller domain. We're trying to discover kind of a way to extrapolate or extend your original function with some values in a new value in the larger domain, so that what you write down becomes a tractable, well-behaved cost function.
Do you have a characterization with final gamma where this 0, 1 over to 1 domain is?
For 0, 1 is tractable if and only if the problem is, well, submodular or trivial. Like either setting everything to 0 is optimal, or setting everything to 1 is optimal, or the problem is submodular. And submodularity is just edge cuts with generalization. Not sure. I mean, there exists a characterization for domain 0, 1, half 1. For a domain of size 3, there exists an exhaustive list of all distinct tractable cases. I haven't worked out kind of the back projection of all of those to the original. They become kind of obscure except the first few. But in general, the way these things work, in general, you will not be able to write down a full list of everything that happens. In general, there's a characterization that says a language is tractable if and only if it is preserved by some algebraic property, and then this algebraic property is kind of inscrutinable, and the exact set of functions which it preserves is kind of inscrutinable, and with some work you can sometimes realize that the problem you're interested in happens to have one of these properties. So maybe, okay, I think I've pretty much sketched on the blackboard here what I'm doing. You have an intractable problem vertex cover that you want to solve. You define the new problem half integral vertex cover on a larger domain. There's some conditions saying this is it's restricted to the original domain. It takes the same values. The new values are not allowed to be smaller than the minimum starting value. And if you have this persistence property, I'm not sure we need to read the definition in detail. Like if there exists an optimum of a relaxation where a variable takes a value from D, then you can assume that this value sticks in the final optimum. So this is a pretty strong condition, but it turns out to be useful. Then, if we have such a relaxation, the exact same algorithm, slightly generalized, as I gave 10 minutes ago now, or more, will work. Like if you have a problem input ik, you just reinterpret it as you replace every cost function in the input by its relaxation. Like you just have a bucket list of, if it's an edge of this type, then this is the cost function I use. So you just replace them function by function. You solve the resulting problem. For example, an LP solver can do this for you. You reject if its solution costs more than k. You pick a variable v. You try all possible actual values in D, like previous just 0, 1, but now let's say all possible values. If there's any direction where the cost does not increase, you can freeze the variable and keep searching. Eventually, there is a variable v where every assignment v equals I increases the cost for integral values I, and you do a branching tree of, well, branches more than 2 directions, but exactly the same kind of tree. If you're clever about a specific problem, you can do a little bit better branching strategy again, but in general, persistence and tractability for the relaxation implies that your original problem has an FPT algorithm by a very uniform scheme. And let me just give a list of some things that work. There is, as I said, a kind of abstract condition. The simplest case of it is called submodularity. So if you take any 2 sets x, y in a graph and you cut the number of outgoing arcs, for example, then the outgoing arcs from x plus the outgoing arcs from y is at least as many as the outgoing from its intersection plus outgoing from its union. This is a very famous classical condition for tractability. So every function, even if it's not just about edges that satisfies this inequality, is tractable. Like yeah, there are several different ways to optimize these. The half-integral vertex cover has some kind of a generalization of this condition. Instead of a search space of 2 to the v, our search space is size 3 to the v, and we replace the union and intersection by some generalizations which do something similar over the large domain. They happen to be tractable and persistent. They happen to solve almost 2-sat submodular cost functions. The half-integral multi-way cut fits into yet another kind of generalization of submodularity for some larger domain, some other way of combining x and y to give 2 new outputs. And it happens that the list of problems that you can solve with this relaxation is well, basically everything where you have some kind of soft bijection constraints between 2 variables, like if u is 1, then v should be 3. If u is 2, v should be 1. If u is 3, v should be whatever third value was. So this is just basically the list of constraints that happen to be that you get if you take your domain here, which is 1 through k and also 0, and you remove the 0 value and look at what's left. So some of these were significant and nasty problems to come up with combinatorial algorithms for. Particularly if you happen to know what they are, unique label cover was kind of a almost tour de force, or at least very genius invention of some graph, randomized contractions, it's called, the first paper that solved this problem. The group feedback vertex set, subset feedback vertex set, odd cycle transversal. It's not essential, I think, that I define all these problems. If you happen to have seen them, you know that they are individually interesting problems which have been solved in many different ways. So yeah, I apologize that this becomes very abstract, but I mean, there is an exact definition that a language is tractable if and only if there is some kind of generalization of the submodularity condition. And you can work out, like, using that condition, you can derive that k submodularity has the persistence property. But that's just like a half page of algebra, which may or may not give any additional insight about how the problem space really behaves. See, where are we? Right, so this was, so this was basically the 2014 paper, journal version a few years later. And this was, so this is still all about this specific property persistence, that just taken this property that happened to work for vertex cover multi-way cut and running with it into larger domains. There is one simpler, or there's a weaker condition that still allows you to build an algorithm. If you have the guarantee that if for every variable there exists an optimum to the relaxation where that variable v takes an integral value, then there's guaranteed to exist some kind of optimum for the relaxation where every variable takes an integral value in that optimum. This is just a statement that if every variable has some integral value in support, then you can just find a solution to your original problem whose cost equals the LP-relaxation. The optimum you get in the lower case might have nothing to do on the surface with the initial assignments. Things can move around arbitrarily, but the same algorithm works. Either you find one variable where every assignment v equals I increases the cost and you branch, or you have a combinatorial guarantee that you're done branching and you have a solution. This was kind of, it's a weaker condition. I don't know a good general way to prove it. It happens to hold that if, I don't even know if I can explain this problem, but if you're optimizing some kind of sum of distances, like you have a metric. Yeah, okay, you have a graph, you have some of the vertices of the graph are locked to values in the metric space. You're minimizing the sum of distances in the metric for placing all the vertices in the space to some values. If your metric embeds in a tree, then you can solve it in 2 to the order of relaxation gap, because it has this property. I helped last year with Felix Geidel. And the name of the condition that these kind of cost functions have is tree submodularity, which is also one of the kind of laundry list of known useful conditions. It's genuinely unknown to me whether this particular class also has the persistence property. If it does, there would exist a slightly faster algorithm, but in either case, it's interesting by itself. I think that this, formally weaker condition. It's if we're asking about when does this work in general, it's better to focus on this weaker condition than on persistence, because persistence might be a kind of accident that holds for some problems, not others. So this is, in particular, yeah. So this is what I was planning to say about this discrete relaxation, the VCSP approach. I'm aware that this is, to somebody who's not used to thinking about CSP-style formulations, this becomes a bit much, because, easily becomes just a long list of definitions. But let me just name some open problems that seem plausible to me. The first obvious question is just simply, for which languages gamma is the VCSP over gamma FPT by the solution cost? So I already mentioned that like almost two-set, vertex cover, edge cuts, and so on are specific examples of the large set of possible VCSPs. It's usually possible, if difficult in this domain, to characterize exactly which are good and which are bad, so FPT or W1 hard. This problem is not the first one to look at, because there are even some individual questions here where we just like change that to define by numerics, like some individual problems which we don't know if they're FPT or not. So if you don't know the answer to some individual examples of gamma, you can't very well derive what the full characterization should be for all questions. It's still a very interesting question ultimately. An easier variant, assume that you start from the relaxation and you ask for which subdomains of the domain of the relaxation do I get a problem, which, an NP-hard problem, which is FPT. So basically saying you have an input is a tractable CSP over a large domain D prime, and you also told which values of D of D prime are the ones you care about. You're looking for an assignment that only uses D. Your parameter is supposed to be the increase of cost by going to the integral value. So this is either polynomial time or FPT or hard, presumably, for every possible gamma prime and D prime. And it might be an easier, more approachable question to try to figure out what's the shape of things here, like what conditions make this tractable. And last question is a more general, it's a kind of different question. So there's a long list of problems which are tractable by the LP relaxation I mentioned, but the relaxation only it works if your functions are built out of small components, like sum of small functions, because the relaxation needs one vertex for every assignment to every one of your functions. So can you minimize the same functions in the value oracle model? Two specific questions which are very interesting. The function class calls k submodular functions over n variables. There has been some research on this, but it's definitely incomplete.
And the other one is just submodularity, where the domain is any lattice with value oracle access. This is known for a few cases. Well, it's known if it's distributive, so it's secretly just a set. And it's known for the if L is the diamond lattice, and I think also for some other one case. It's not known in general if you can or can't. It seems an interesting question. It's also plausibly quite difficult. Any further questions about this part? Yes, I'm happy to discuss any of this afterwards if you have any questions. So I just want to again, without going to technical details, I just mention what you get in the. This is a completely different result. This is now from SODA 2017. So now we're going to start defining a purely combinatorial axiomatic condition, which turns out to define tractable problems. Definition: a biased graph is a graph together with a list, abstractly speaking, of cycles of the graph, not induced cycles, but simple cycles, so what you normally think of as cycles. Every cycle in B is called balanced. The cycles not in B are unbalanced, and the condition says whenever you have a theta graph, so this is kind of 3 paths between U and V, which contains 3 different cycles, it's not allowed that only exactly 2 of these 3 cycles are balanced. So if 2 of them are balanced, the third one has to be balanced. So B will be given as an oracle that you ask it about a simple cycle. It says balanced or unbalanced. There may or may not be some representation or description abstractly, but in the extreme case, this is just an exponentially large list of yes and no. So it's an oracle. For us, the more interesting direction is to say, complementarily, if you have a theta graph where, let's say, the outer cycle is not balanced, and if you draw any chord, so U and V is either an edge or a path from U to V disjoint from the circle, at least one of the 2 resulting half cycles or new cycles is also unbalanced. And for example, in this formulation, you can think of the red cycles as having odd length. So if the red cycle is odd length and you draw any chord or chord path, you cannot split an odd cycle into 2 even cycles. That just kind of, in this, one of these has to be not even. Or you can say the red cycle is any cycle whose length is not equal to 0 modulo 10. Same argument holds that whatever the length of this one is cannot split into 2 lengths equals 0 modulo 10 because modular calculus is a group. So you can invent several different interesting special examples of this kind of class. So it's just if the red cycles will be obstacles to us, if the model problem to think about is odd cycle transversal or killing all odd cycles, our useful property is if you cut an obstacle in half, at least one resulting smaller piece will also be an obstacle. These define something called frame matroids, which, as far as I know, is purely accidental to us. We will not use any matroid connection, anything except the formal definition. Now you can ask, given a graph G and pure oracle access to the class of balanced cycles, can you find a set of at most k vertices which hits all unbalanced cycles? So all odd cycles or all cycles whose length is not divisible by 10 or other things which we'll get to in a second. feedback vertex set, every cycle is unbalanced. That's a special case of this. Odd cycle dispersion, just mentioned. A problem subset feedback vertex set. You want to kill cycles that contain some, intersect some special set of vertices, S. If you have a cycle through S and you have a chord, obviously at least one of the two parts still intersects S. So this is also one of these examples. You can decorate your graph with elements from a group and say that a balanced cycle adds up to identity of the group. If you've seen it, you've seen it, but it's an incredibly interesting formulation. It also happens to have this property. And you can get node multi-way cut. Maybe it takes too much time to detour through that, but you can kind of add one new vertex artificially, which will be the center of all your cycles, and now it neighbors or return a cycle through the new artificial vertex is exactly a path through two different terminals. So multi-way cut is also an example of this problem class. And extremely surprisingly, you don't need any more assumptions about the biased graph class other than oracle access yes, no in order to solve this. It seems on the surface that it should be able to hide some unbalanced cycle somewhere it can't get to, can't find, but this condition somehow means that you don't need anything more than the oracle access. So for every biased graph, we can solve the cleaning problem in 4 to the k time using an LP solver. This will be with not an explicit LP, but like ellipsoid method or something, or separation oracles, and membership access to B. The way it will work, I can't go into any details, but the general scheme, you can think of it as a walled garden approach. The whole world is kind of messy and scary, but if we start at one point, we can build a local area that's nice and well behaved. So we start at one vertex, we clean up all the mess that's near to us, and eventually we decide that we want to separate ourselves from the world by cutting all vertices that surround us. Once we have some useful region. So we grow a region around a root V0 using the LP. We delete all the neighbors of a region and we start over with a new root. Eventually, once we've done this, the graph has become completely decomposed into balanced regions and you have solved the problem. The rooted version of the problem is perhaps slightly unobvious. Well, ultimately, okay, in the 0-1 world, you're really just looking for deleting some vertices such that no bad cycle, no unbalanced cycle can be reached from the starting vertex. But half integrally, okay, yes, this particular problem that the connected component of V0 and G minus X contains no unbalanced cycles, has a 2 approximation of 4 to the relaxation gap algorithm, and can be solved in time 2 to the k. So this is just once we define an LP relaxation for this, it will be half integral and persistent and all the things. Yep. If it is, I mean, the answer is yes, maybe, and no. No, in the sense that there exist biased graphs that can't be represented by, well, certainly not by turning them into group labels. And I think you can probably also get that you can't get I mean, I don't know of any other way to get a VCSP. If you have group labels, you can turn it into VCSP, but the domain becomes the size of the group, which might be exponential. So that's the maybe. If you can do it with a small group, then you have a VCSP.
So these are very similar to the problems we solved last time. It's just...
So if you allow like arbitrary doing this, you can always do something.
No, I mean, I think there are some biased graphs you just can't turn them into local constraints because the balancedness is a global property that doesn't allow itself to be isolated. I don't have a 100% statement of this, but I think it seems very plausible given the literature that this is the case. It's a usual thing as in matroids, like they're just axiomatically defined and therefore they don't observe any representability properties unless you force them to. And I think that's the shape of it. So let me just paint as a picture what is the LP relaxation for the rooted version of graph cleaning. The yellow part is supposed to be the local region we have grown so far. So we start from the center and we solve an LP. An obstacle consists of an unbalanced cycle that's not separated from the root yet. So the obstacle consists of a combination of one unbalanced cycle and one simple path from the root into the cycle, where in terms of the LP, you break this balloon into two paths, the red and the blue, and the sum vertex values along the red path plus vertex values along the blue path sums to at least 1. So it's a non-obvious and obscure LP relaxation. If you assign value 1/2 to a vertex on the path, then it's counted both as red and blue, and it counts as having sufficient to kill the cycle. Otherwise, you have to either assign 1/2 to 2 different places, or the value 1 to some vertex on the cycle. So it turns out that if you think about the LP where you just enumerate all possible balloons as an exponentially long list of constraints, it turns out that this LP is half integral and has the persistence property. We can optimize over it. We can optimize over it using, well, this is called the separation oracle. Right? If we have ability in polynomial time to find one violated constraint, then we can solve the LP in polynomial time. And if you think about it, in the first case, if you fix the cycle, you only care about shortest paths from the root to the cycle. There's no reason to think about constraints that take a longer, more expensive path to reach the cycle. There's a stronger conditions you get by the there's a stronger conditions which you get if you just mess around with it because of the closure property or the property of unbalanced cycles. That, for example, if you think about the effect of adding this path, some other path from this into the cycle, then these two paths and these two paths form a chord for the cycle. So if this happens to also be a short path, then either just this thing or this thing is also a unbalanced cycle. So you get kind of, in a way that's non-obvious, that follows. You can find you can find a balloon of this of weight less than 1 by shortest path queries. It turns out you can always just pick one edge on the balloon, ask for the shortest path to the one vertex, shortest path to the other vertex, and ask if they add up to the value less than 1. And if you disturb your assignment by arbitrarily ordering the vertices to make the shortest path unique, then this is a polynomial time way of finding a bad unbalanced cycle. Despite it being just oracle access, all I need to do is to ask for a shortest path for every edge of your graph, or two shortest paths for every edge of the graph, and ask the oracle if it's balanced or unbalanced. So this is the first of what to me is kind of just accidents about this problem. So that, as I said, the condition of biased graphs was known from the literature, and it's just a list of combinatorial accidents. If you phrase the LP this way, it happens to be half integral and persistent and oracle optimizable. So the separation oracle I sketched, half integrality, does follow. It's very close to node multi-way cut proof, actually. And persistence is a strange thing, but I will not dive into it. Assuming that we are able to solve, well, local persistence is probably clear enough. It just tells you you're able to find a cheapest way to isolate the root from the rest of the world. But the problem is, if you think about what you need, you're not really solving the rooted problem. You're solving the original problem without roots. You need the property that whatever solution you find locally will be contained in a global optimal solution. There's a step from local to global. And again, both the half integrality and particularly the local to global step of persistence, both things hold using only the axioms of biased graphs. And I couldn't really give any. For the half integrality, I could hand wave a reason for why it should be half integral. For the persistence, even having written the proof, even though the proof is not extremely long, I couldn't hand wave my way around why it holds. It just, something happens. So the persistence locally is that vertices at distance 0 from V0 in the LP do not need to be deleted globally. Vertices which are actually deleted in the rooted problem can be deleted globally. So these things add up to a 4 to the k algorithm for original problem. Related but not identical. Iwata, Yamaguchi, Yoshida had a problem, they call it 0-1 all problems, where you can similarly define a well-behaved set of forbidden walks in a graph and solve it in something like 4 to the k times linear time. The way this works is by this indirect arrow for the start of the talk. You can replace the LP solver by a highly involved packing of half-integral bad paths. This can be done in linear time. And it essentially covers the intersections of the problems of the first and the second part of the talk. So this does not cover general biased graphs. It just happens that the interesting cases we mentioned also are examples of group feedback vertex effect. They can be turned into group labeled graphs. And for those, case of modularity and this oracle holds. Last set of open problems. This talk has been full of annoying coincidences. Another coincidence, biased graphs. The condition of biased graphs happens to be the defining property of an extremely important class of matroids, many of which are representable. Representable matroids happen to be extremely important in interesting and non-trivial conversation algorithms. For example, for the problem node multi-way cut with a constant number of terminals. It happens to be the case that I don't know how to exclude the existence of polynomial kernel for any, certainly not for any rooted problem, version of this problem. That's a lot, that's just a, are these coincidences or not? Is there some link where you can use the kind of, is there some link which tells you that some of these problems have polynomial kernels? The second question, feel free to try to generalize the 0-1 all half-integral path packing to packing of balloons in rooted biased graphs. Iwata told me that he tried and concluded it was too unwieldy and messy. So it's not easy. So it's either extremely messy or extremely difficult to come up with, or both. But it may very well be possible. Thank you.